Hello everyone, this is Professor Hu. In this lecture, I will introduce how to construct a circuit from a truth table using the algorithm called sum of products. A logical statement is a statement that evaluates to either true or false. For example, the sun is shining is a logical statement. Boolean logic combines multiple logical statements into an expression that is either true or false. Boolean logic is also binary logic. We use 1 for true and 0 for false. Boolean logic rules are shown in the figure for AND, OR, and NOT. In logic AND, 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. That means AND logic requires both are 1 and result is 1. In logical OR, 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. That means in logic OR, either operand is 1, result is 1. In logic not 0 is 1, not 1 is 0. For convenience, we use different writings to represent this logic as shown at the bottom of each logic. We use symbols to represent the logic. For the three fundamental logics, we have the symbols listed here. The left one is the AND gate. The AND gate has a straight input and round output. Sometimes we use a dot in the middle of the shape to indicate an AND gate, but the dot is not necessary. The middle symbol is OR gate. The OR gate has a curved input and sharp curved output. Sometimes we use a plus sign in the middle to indicate an OR gate, but the plus sign is not necessary. And the NOT gate consists of a triangle and a small circle. And below the shape, the symbols, we have the truth table indicate that these symbols represent the three fundamental logics. We can implement the logic using circuit gates. The NOT gate needs one transistor. When the input is at a high level, the transistor is conducting so that the output is pulled down to the ground. Therefore, the output is at a low level. When the input is at a low level, the transistor is blocking so that the output is kept up to the power. Therefore, the output is at a high level. The result is the output always has an inverted state to the input, so that it is a NOT logic. The AND gate can be implemented on a NAND gate. A NAND gate can be implemented with two serially connected transistors as shown in the figure. In the NAND gate, when input 1 and input 2 are both at a low level, both transistors are blocking. The output is kept at a high level. When input 1 is at a low level, input 2 at a high level, the upper transistor is blocking, though the lower transistor is conducting. The output is still kept at a high level. When input 1 is at a high level, or input 2 at a low level, the lower transistor is blocking, though the upper transistor is conducting. So the output is still kept at a high level. When inputs 1 and 2 are both at a high level, both transistors will be conducting. So the output is pulled down to the ground. Therefore, the output becomes low level. That forms the NAND logic as shown in the NAND logic truth table. Based on NAND logic, once we add a NOT gate on the output, that inverts the result of output. Then the three transistors form an AND gate. We can see the truth table on the right upper corner for AND logic. The OR gate can be implemented on a NOR gate. A NOR gate can be implemented with two parallel connected transistors as shown in the figure. In the NOR gate, when input 1 and input 2 are both at a low level, both transistors are blocking. The output is kept at a high level. When input 1 is at a low level, input 2 at a high level, the right transistor is blocking, but the left transistor is conducting. The output is pulled down to the ground by the left transistor. So the output is at a low level. When input 1 is at a high level, input 2 at a low level, the right transistor is conducting, though the left transistor is blocking. The output is pulled down to the ground by the right transistor and is at a low level. When inputs 1 and 2 are both at a high level, both transistors will be conducting, so the output is pulled down to the ground. Therefore, the output becomes low level. That forms the NOR gate logic as shown. Based on NOR logic, once we add a NOT gate on the output, that inverts the result of output. Then the three transistors form an OR gate. Generally, we use truth tables to represent Boolean logic. In the Booner expression, we use 1 for true and 0 for false. Since we can use gates to implement the three fundamental gates, we can use gates to implement any Boolean logic. Generally, to construct a truth table, we can determine the number of rows based on the number of inputs. Since each input could be either 0 or 1, so one input needs 2 rows. 2 inputs needs 4 rows. 3 inputs needs 8 rows. And n inputs need 2 power n rows. And here we show an example of a truth table. There are 3 inputs, A, B, C, and we can list 8 rows. And for each of the rows, suppose we have 2 outputs, output 1 and output 2. Each of them have a combination of values from input A, B, C. For example, output 1, when A, B, C are all 0, it is 0. And when A is 0, B is 0, C is 1, it is 0. When A is 0, B is 1, C is 0, it is 1, and so on. For output B, when A, B, C are all 0, it is 1. When A is 0, B is 0, and C is 1, it is 0. When A is 0, B is 1, C is 0, it is 1, and so on. So that means each of the outputs are determined by the combination of the three inputs in this example. And we are going to construct circuits to implement the truth table for the logic. How to construct a circuit from a truth table? Once we have a predefined truth table, we need to figure out a Boolean expression to represent the truth table. From the given truth table, we will construct a circuit to implement the logic in the truth table. We need to consider each output separately created by all its inputs. Let's first consider output 1. In output 1, in the 8 possible cases, we can see there are 2 cases that output 1s. According to the sum of products algorithm, we need to construct Boolean expressions for the cases that output 1s. Why? Because other combinations of our inputs do not affect the output. When A is 0, we say it's not A, and represent it with a apostrophe, with A apostrophe. For case 1, the input combination is A apostrophe and B and C apostrophe, means not A and B and not C, because the inputs A is 0, B is 1, C is 0. We negate an input for 0. The result is a product format of 3 inputs. Similarly, for case 2, the input combination is A, B, not C, because the combination is 1, 1, 0. Finally, we sum up the 2 cases and obtain the result. Output 1 equal to not A and B and not C plus A and B and not C. The result, a Boolean expression, is the sum of the products of the cases. For the given Boolean expression, output 1 equal to not A and B and not C plus A and B and not C. From this Boolean expression, we know that we need 2 3-input AND gate and 1 OR gate. We can easily construct a circuit to implement it. We first need to draw 3 inputs, A, B, C. And for not A, we need an invert gate or NOT gate. For not C, we also need an invert gate. Now, first for the AND gate. The first AND gate input is not A, B, and not C. So we connect not A to the first AND gate, and then connect B to an input pin of the AND gate, and then connect not C to a pin of the AND gate. The second AND gate, we connect A to a pin, and then B to a pin, and then not C to a pin. And finally, we need a two-input OR gate. So just use the OR gate, connect the output from the two AND gates. And the output from the OR gate is output 1. And this is the circuit that implements output 1 of the truth table. And similarly, we may easily construct a circuit for output 2. And output 1 plus output 2 will be the implement of the truth table. Actually, we may simplify the Boolean expression by combining the common items. For example, output 1 equal to not A and B and not C, or A and B and not C. This equals to not A or A, then combine B and not C. And finally, it is B and not C, because not A and A is 1. Then the circuit can be simplified as below. Just B and not C through an AND gate, we get output 1. You are not required to simplify the circuit. Then we can use a drawing tool to draw the circuit. Suppose we use TinyCard, which can be downloaded from the internet. Search the internet, then download and install TinyCard on your computer. TinyCard is a kind of tool that can be used in professional field. So it's not just for class learning. Thanks for watching.